Timing is pretty good. 9:56. You're first up.
Yeah, I'm again.
Okay. Please proceed.
Okay. So no more talk about the school. So I'm Sebastian Geiger. I'm one of the energy simulation chairs here at TU Delft. And what I've been trying to do with the students and the postdocs here at TU Delft in my previous life, so trying to integrate geoscience and reservoir engineering better to make sure that we get the right bit of geology into our reservoir models. At the end of the day, we make more meaningful predictions with our reservoir models, and we try to de-risk some of the operations. And what I want to do is I want to show you one particular application using a software that we've developed in partnership with Peel College London, open source software, and University of Calgary called Rapid Reservoir Modeling. You've seen me perhaps speak about the software in the past. I'm going to talk about how we use that software to do some very fast assessment of geological uncertainties in the carbon capture and storage world. Why do we want to do this? Well, geological reservoirs are heterogeneous, and geological heterogeneity is the key determining factor on fluid flow. And ultimately, our understanding of geological heterogeneity influence how we try to manage the reservoir, how we try to de-risk a reservoir, how do we optimize production or storage in a reservoir. The geological heterogeneity is always multi-scale, it's complex, and our information is very limited, so that there is an inherent uncertainty. We do at the end of the day, where we try to solve and get our way around the problem by building a reservoir model. And what we sort of forget quite often along the way is what the purpose of a reservoir model is. We want to use the reservoir model to visualize the reservoir, calculate volumes, storage space, for example, use input for flow simulation, plan wells, forecast rates, and ultimately explore some of the key uncertainties, the key technical risks, and try to de-risk the project. What we don't want to do is build a reservoir model just because my PhD advisor told me build a reservoir model, or somewhere down in the workflow, in the company workflow, someone told you you have to build a reservoir model to make a regulator happy. Mark Bentley coined this modeling for comfort. So really, a reservoir model always should have a purpose, and not just because someone told you to do this. And this is a reservoir model we've built with students in the past. It's a real reservoir model of a real field. What we sort of need to remind ourselves is one single grid block, maybe about 100 by 100 meters in size, a couple of meters thick. So that grid block contains tens of thousands of tons of rock and thousands of tons of fluid. We sort of assume the uniform properties inside this grid block. Along the way, we sort of hope that all these beautiful geological heterogeneities, we somehow capture them adequately in our reservoir model. Quite often, we don't. These days, we have big computers, and yesterday, heard about people can now build grid block or reservoir models with billions of grid blocks. But if you're not careful, all that we do is we spend an awful lot of time, an awful lot of money to build models that are precisely wrong, not approximately right. Because the data that we have isn't equal to the models, isn't equal to the truth of our reservoir system. And Hardy gave a really nice example yesterday, the fluid flow benchmark. You said, Hardy, my colleague Dennis and I, we were going to the same school. We have this really well-constrained problem. We still see the same data very differently. We come up with different models, different interpretations. So we're not only having the uncertainty in the data, we have also uncertainty in how we understand and interpret and model data. So data is just a small set of a reservoir system, lots of uncertainty associated with it, lots of uncertainty how we see the data, how we interpret the data. And Tim Bars, one of the postdocs who just had a really nice PhD defense 2 weeks ago, it's a big discussion with your examiners who all have different geological backgrounds. They all saw the geological data, the same data, very, very differently because of the inherent bias, what they worked on in the past. So what we want to do is, what we really need to do is, for a project, think about different models, different interpretations of the data, not just the uncertainty in the data itself. Now, this is where Rick came in and said, yesterday, I'm paraphrasing Rick, is this reservoir modeling business is all a bit of magic, and it is in that sense. Now you do this for very data-poor environments like a saline aquifer. We have Andrew's 7-day well test, and that's about it. And then Eric showed this really nice picture yesterday and said, well, here's the southern North Sea. Now we have oil and gas production, oil and gas license. We want to build wind farms. We want to do CO2 storage. We want to do hydrogen storage. Lots of fighting for acreage. We need to do this quickly because by 2050 we want to be net zero. Hardy mentioned, well, 10-year project, 15-year projects. We really need to start doing this now, not just in the North Sea, in every mature basin around the world. So it becomes magic on steroids. So what we're trying to do is do this a little bit different in RRM and say, use this old adage, if you can't draw it, don't model it. So if you can draw your geological concept, then you understand what you're trying to build, what you're trying to do with your reservoir model. If your model looks nothing what you have drawn, then probably your model is wrong to begin with. If you have another geological concept because you want to look at the same data in a different way, do a different testing of the data, you may need a very different geological scenario, maybe more than one scenario. But again, now we want to do this for lots of basins, very quickly, very fast. The current tools that we have don't allow us to do this because at the end of the day, we need the what was it, Rick, 2.65 factor. So Andrew is going to invest very heavily into your project. So what we have done in partnership with Calgary and Imperial College London is to develop the Rapid Reservoir Modeling open source platform. The concept is very simple. It's to do what geologists have always done, is to draw geology. And what you can do in the software, and if you want to learn more about the software and see it in action, talk to Kylie, Guofeng, Santosh, and to some degree Eli, who's sort of using the developing workflow so you can tease out geological information and link them to the flow dynamics. So what you can do in RRM, you sketch geology on your computer, and then so a bit by magic, this is where the real magic comes in, it builds geologically consistent models in real time. We use something called sketch-based interface modeling, which has been around computer science for over 20 years. And this technology takes two-dimensional sketches and the information from these sketches to obey geological rules to build a 3D model. So the models that we built, the geological models, are simply descriptions of surfaces. These surfaces then define the geological heterogeneity. There is no grid to begin with. The grid is only created on demand. When we want to do some calculations, we do some very fast calculations at the end of the day to get a feeling of what are the storage volumes, how fast could fluids move through the reservoir. Only very approximate. We still need to do the detailed modeling afterwards, the detailed dynamic modeling, our favorite simulator, be it Darsim, be it CMG, whatever it is. So in RRM, we describe geological heterogeneity by a set of hierarchical surfaces. We don't care what scale we're looking at, the basin scale, the outcrop scale, somewhere in between. So geological heterogeneity is modeled as one or more discrete rock volumes that are bounded by surfaces. These are geological domains. The hierarchy of surfaces, faults, stratigraphy, facies, they're genetic bodies across multiple scales. The transport properties, the petrophysical properties, they're constant within a geological domain. That's exactly the same thing we do in grid-based reservoir modeling, but now we have a meaningful volume, a meaningful domain, not just a grid block of some arbitrary size. And in RRM, so we have then geological rules in these sketch-based interface modeling operators that make sure that the models we build are geologically consistent at the end of the day. Here's an example. So this is a fault and thrust belt in Borneo. So the typical data that you have in data pool environments like CCS, like geothermal energy, 8 seismic cross-sections, that's about it. You want to do, and what we wanted to do is to say, well, where are the fault locations? What's the reservoir closure, spill points, leakage risk, drilling risk? Do this very quickly, work through the same data and do different interpretations. So we use RRM, and you see a little video where we now have sketched a model. You see the seismic cross-sections popping up in the background. We interpret it. In between, RRM interprets in a geologically consistent way the different surfaces. That model took us 30 minutes to build in RRM. It's probably taking a little bit longer in your favorite geological modeling software. Once we have built our models, we use something called flow diagnostics that Knut Andreas Lee at Syntef and Chevron were involved in this, have pioneered. So create a grid on demand. We do some very fast calculations that take seconds to do, even if you have millions of grid blocks, to do some very quick approximate dynamics, obtain some very quick approximate dynamics of the reservoir behavior. Things like the reservoir pressure, swept-drained reservoir regions, displacement efficiency, and other properties, all based on fast steady-state approximations, not to take things away from Darsim, from DARTS, from CMG, your favorite reservoir simulator, just to get this first quick look of how the reservoir could behave. Again, here's a little example. Very vertically exaggerated fluvial channels, replacing some wells, and this all happening in real time. You can see we're copying wells here. You drag the wells around, you change your completion. Rick, you had 4 completions in Aquistore. You change your completions, and you see how the reservoir behaves. Where do the fluids are going? How fast are the breakthrough times between different injector and producer pairs? It all happens in real time. So you build your model in 30 minutes. Now you get some first dynamic information of how your reservoir could behave. And you can sort of hone in some of the scenarios that you want to test later when your real magic comes in with your favorite simulations. Yesterday we talked about pressure evolution. One of the big things is, Rick, you said 2 kilometers is the average radius of the CO2 plume. Pressure goes a long, long way out. So in previous versions of RRM, we used something that Mike King, who was an energy simulation chair, developed, the diffusive time of flight concept, which allows you to quantify how fast the pressure front moves through the reservoir in a very, how far the pressure front moves through the reservoir in a very, very fast time. So we implemented this in RRM, and we need to dust off that code again to make sure that we can look at things. We have a storage space, and how do different, in a basin, how do different wells interact with each other, how do the pressure fronts move, and when do they start interfering with each other. Just to talk you through a couple of examples, this is a theoretical example. I'm going to show you a real-world example. So this is a shallow marine example. The booklets information, you have 5 logs that have been interpreted. We know where the logs are. Their position, we know the average dip direction of the facies. That's all that we know, and we now want to interpret this. So what we've done, we've created in RRM in an afternoon a number of geological scenarios. On the left-hand side, on your left-hand side, you see so the base, the first scenario, you see so different layers stripped out. On the right-hand side, you see different interpretations of the same data. So they're all honoring the data. They're just the different ways we see the data. You immediately see what the pore volumes are from the different facies. I want to key you in on this light yellow facies. And so that's the one with the most to the left yellow color, which has a very small pore volume. That's the foreshore facies. Very small pore volume, but dynamically it's going to be a very important volume. Again, Rick, sorry, I keep picking on you. No, you love 3D printing. You can 3D print these models because they're surfaces. So if you want to explain to your power engineer from Saskatchewan or from Scottish Power, say, how does a reservoir look like? You print your model, and they can puzzle it together. And we have done this as educationally, actually a really interesting example. Now we take the flow diagnostics approach and say, well, where, if you inject CO2, and this is no gravity, this is no viscous fingering, this is no two-phase flow, it's just a first quick look. Where would the stuff that we inject, in which facies would it go preferentially? And now this foreshore facies that has a very small proportion in terms of reservoir volume suddenly becomes quite important, because that's what most of the CO2 goes, a significant portion of the CO2 maybe going in the first years of injection. So that tells you something about where do I want to spend my efforts in terms of reservoir characterization, in terms of the understanding some of the reservoir properties in more detail before I start switching on my CMG simulator, and before I go do the rel pumps, do the geomechanical experiments, and so forth. And again, this is a little animation here. You have a CO2 injector well, and you see as time progresses, where does the CO2 or the injected fluid goes, and you have this pie chart there that shows you as time progresses which facies is taking up which proportion of the fluid over time. Again, not to replace the real physics, it's just to have that very first quick look of what you can, what could happen in your reservoir. We know that we're simplifying physics a lot, so we do have some measurements, things like the gravity number to look at viscous versus gravitational forces and see where our physics approximated accurately by doing viscous dominated flow, and where do gravity forces become very strong, for example. So we know that once the fluid has reached these parts of the reservoir domain, then our prediction is really off, because gravity for the given well controls becomes so important and becomes too dominant. And again, what you're seeing here is the same reservoir, and just to emphasize, now this is a very large reservoir, several tens of kilometers in size, just a few tens of meters in height. Now let's go to real scenarios. This is the Northern Lights project. It's this big CO2 storage project in the North Sea that Shell, Equinor, and Total planning to operate, and some of the CO2 that's being produced here in the Netherlands. I think it's a cement factory, or is it a fertilizer factory, is shipping. It's one of the first customers to ship their CO2 to the Northern Lights project. So that is deemed to be one of these central CO2 storage hubs in Europe. Shallow marine Johansen formation, you think it's really reasonably well characterized, but it actually isn't. So one of the big things the geologists don't know is, and you see this on the top picture here, is what's actually the geometry of the old shoreline geometry. Is it sort of more accurate form that you see in the Model A, or is it more spit form that you see in Model B? And the other uncertainties, what's actually the dip angle of the clinoforms? How much cement and how much interfingering of the facies across these clinoforms are there? What's the degree of bioturbation? These are things geologists don't know that all could potentially impact reservoir behavior and the spreading of the CO2 plume. Is it 2.1 kilometers or 1.9 kilometers? That's what we're after. So what we've done, this was a master's student in Peel College London. This is what really excites me, is that master's student has never heard about the Northern Lights project, has never looked at the geology, has never used RRM, and within 7 weeks, he built the models, he analyzed the models, he got results that are worth a really nice publication. He reported all the results through a publication. So, and Will Jackson, a master's student, Peel College London, used RRM, experimental design with 32 different reservoir models over a few afternoons that look at all these hierarchical geological uncertainties, and then use the flow diagnostics, look at the impact on pore volumes and where could the CO2 plume approximately go depending on which flow direction we have. As I said, that was done, the entire work was done in a few weeks. It would probably take a little bit longer with existing workflows. So we have two scenarios for the two different shoreline geometries. There's more accurate form, the spit geometry. And we have in one scenario we assume the plume goes from left to right, so we set the well controls. The plume is moving from left to right, and once it's north to south, we see so the time at which the plume spreads and the facies that the plume is invading. Again, it's not the real physics, but it's his first quick look. And you do this for all 32 models, and you do your uncertainty analysis. On the left-hand side, you see the impact of pore volumes in terms of geological uncertainties, and it really doesn't matter. In terms of storage space, whatever you have in terms of reservoir architecture, doesn't really matter. That's really dominated by your petrophysics that you put into your reservoir model. But in terms of where the CO2 plume goes, depending also on which flow direction you assume, north to south, east to west, and you see that things like the dip extent, the clinoform dip, the interfingering, that really influences the flow direction of your CO2 plume and the speed at which your CO2 plume moves. This is really valuable information because now I can go back and say, actually, I do have some seismic data. Maybe I want to reprocess that seismic data. Maybe I want to call up Eric Verschuur, get it from TU Delft, get the seismic data reprocessed to reduce some of these uncertainties and build a reservoir model that's more meaningful before I start switching on my favorite commercial simulator. So now we put ourselves in a position where we know what data we want to look for and how we can so that we can design our full physics simulations in a more meaningful way. So to summarize, geologists were born because engineers need heroes too. When we build reservoir models, we need to see the geology of the reservoir model like the fluid does. Quite often the geologists are really exciting about this tiny little bit of bioturbation that I want to put in my reservoir model. And it just doesn't matter. The fluid couldn't care less about one type of fluid, couldn't care less about that bit of bioturbation they got really excited about. So we really need to think about the geology like the fluid does, like the fluid sees the geology. We need to think about how we use that knowledge, how we integrate this knowledge into our reservoir models from day one for subsurface storage applications, for geothermal applications, in situations where we have big data scarcity, with a big picture, where we need to get the big picture right because we need to do this over and over again for many geological basins, and in data poor environments, and do it in a very, very fast way if we really want to have a crack at decarbonizing. Open source RRM, so this is open source, you can download it, can help you to explore some of these uncertainty from the get-go with the aim to design some more meaningful reservoir models. The last bit of information, really what we need to focus on, make sure we're approximately right and not precisely wrong. With that, Thank you to the sponsors of the RRM project. Thank you for listening, and happy to take any questions.
Thank you, Sebastian. Any questions on the floor? Yes, please.
Bo Zhang from University of Alberta. Great work, Dr. Geiger.
Thank you.
RRM works like a magic.
Well, it's not.
I'm just
not
quite
magic.
interested from structural modeling. After
Yeah.
that, how would you determine the petrophysical properties and geomechanical properties?
So it's a good question. So in terms of petrophysics, so the geological domains in RRM, at the moment we assume there's a uniform property in a geological domain. So if you have foreshore, if you don't know in a data pool environment what your porosity is, why do you want to start sprinkling some magic fairy dust of geostatistics onto that foreshore geometry if I don't know what the data is? So it's really, go back to the base, say, well, let's take the average porosity that I know in that setting, dial it up, dial it down, see what it impacts storage volumes flow. Same applies for the geomechanics. We do have actually, we had a PhD students in the past, and we haven't linked this to RRM, so we adapted the flow diagnostics framework to also account for some very basic geomechanics. Again, with apologies to Rick and Giovanni, this is not the proper geomechanics, this very first quick look to understand if the reservoir would deform, what happens to your flow behavior, what bits of data could really make impact on how the reservoir behaves dynamically. Hardy mentioned yesterday, we don't know what the constitutive models are, so you can look at different constitutive models, very quick calculations, in a couple of minutes, get this feedback. Again, we use the same approach, constant property in a region. If you want to put more heterogeneity, don't sprinkle geostatistics over it, put your geological thinking cap on, draw another surface in there, because then you want to make an informed decision rather than sort of get the fault security due to doing a lot of geostatistical work. This is not to knock off geostatistics, to do this quick screening, geologically informed decisions, but with this fault security of working through big statistical models and approaches.
Very interesting. Actually, we have a project with Chevron. They have the Comstrat model, which is a dynamic grain size models, which use structural geology to model those structural bodies. And we are pretty much very puzzled how to convert the grain size dynamic into the geomechanical properties or the flow properties. I think probably that's a good idea to maybe for the structure body, we assume a constant at the beginning and then use the statistical method and then trying to populate that.
But then you get into the upscale of geomechanics, and
Yeah, it's
I'm like, I'm out of my depth here. I mean, I'm generally out of my depth, but then I'm really, really out of my depth. But for me, the question is always, what's the value of data? So it doesn't make, at the end of the day, if I want to get Andrew to invest into Rick's project, billions of dollars, does that data point really swing the decision? And that's if I have constitutive model A, constitutive model B, where does it compare in terms of the different uncertainties, or the things I don't understand about the geology and the geological heterogeneity, the things I don't understand because I'm looking at the same data in a very different way than Hardy does, and Eric does, that Tim does, and Andrew does. So, and that's of putting out, testing those scenarios to look at what is really the data that we need to collect, the bit of research that we need to do, get done properly. That's for me really, personally, very important question.
so in RM right now for each structure body, the geomechanical properties or the flow properties is from existing understanding, like log interpretations.
From an existing data set. So from the Northern Lights data set, we knew what are the average porosities, for example, for the different facies in the Northern Lights project, and then we just plug them into RRM, and there's a little script you can predefine them, or you can do this manually, and then you do your calculation, and you can check if the porosity, average porosity 25%, well, what happens if it's 30%, what happens if it's 20%, does it change our understanding of the reservoir behavior in such a fundamental way that I need to really invest in getting that property nailed down or do more lab experiments, etc.
Thank you very much. Works
You're
like a magic.
No, I'm not sure. Talk to Kylie, talk to the guys who use it, and they can tell you about all the bugs that keep cropping.
Right, that's magic on steroids, you said. Question online.
Yeah.
Hi, Sebastian. This is from Ali Papi. You may know him. Hi Sebastian, nice talk, thanks. Your model looks pretty much similar to the software I used at Imperial for my MSc with a group of Professor Matt Jackson.
Yeah, because it's Matt and I are collaborating on
Exactly.
that
So it's
project.
IC-FCRST, Imperial College Finite Element Method, right?
So what Ali is referring to, so RRM is the geological modeling part, and then and Matt Jackson and I was of the PIs on the RRM project. What Ali is referring to is Matt is also having a code called IC First, which is a finite element, finite volume code that uses surface-based geometries and then uses unstructured gridding, adaptive grid refinement to track fluid fronts. So it's a different dynamic simulator that Ali is referring to. This is the geological modeling part.
Okay. And your geological go ahead.
Yeah, Suzanne Herter, TNR and University of Queensland. Maybe it's a little bit sort of an additional comment that I like the idea of the geologists as heroes for engineers, but what this is telling me is that the real skill starts with understanding your depositional environment, understanding the frequencies of different facies, their dimensions. So basically, I think that's the first step that goes into that. And it's brilliant that you can then collect that knowledge into a visualization step that then can lead to everything else. I think that was a real gap that was around for quite a while.
Thank you. Yeah. I buy you that drink afterwards, Suzanne. You get one too. You get the coffee here. The other Susan.
Right. So that's exactly, probably quite a few years ago, when people talk about having a geological model, complicated geological model, running multiple, say 1,000 realizations, and do not know which one is the one to use. And then they would run streamline simulation, histometric total production, oil, water, gas, and say, among the 1,000 scenarios, realizations, this top 5 would be closer to it. But you have simplified the geological modeling aspect and have the faces, everything object-based, drawn up, and then model that a lot faster.
Yeah. This is not to replace your standard G&G workflow. This is this pre-screening step that once you spend all this effort of building these detailed reservoir models, then where I've looked at these 3 different phases interpretation, 2 just in terms of storage volumes, in terms of approximate reservoir behavior, they just give exactly the same result. So just take one. Now these 2 other end members, these are the ones I really need to consider until I get my production data, until I can start the history matching. Yeah. And I'm not, Hardy mentioned this yesterday, you get the right answer for the wrong reason. So you start off on the wrong path, and you've missed that key bit of geological information very early on because you locked in your concept. Yeah. And yes, I've history matched it, but every time I try to predict what happens in the future, my history match or that prediction is really off. And I've seen models where people have put donuts around wells to get the wells, like literally donuts around wells to get the wells performing. I think this has nothing to do with geology, but gives me a good history match. Yeah, let's bring the geology back into reservoir engineering.
Right. Good point. We have one of our directors, Dr. Bob.
Okay, yeah, Bob Gokenheier, one of the directors, former BP. I love your talk. You're taking me back about 20-some years whenever Amoco and BP was merging together, and our chief technology officer was a geoscientist who was very skeptical about the business value of reservoir engineers because all he knew about us is we were precisely wrong. Okay, and so I love that buzz phrase. You should write this down, publish it, and make sure every young reservoir engineer who's pretending to use a reservoir simulator understands this. Okay, so we developed a reservoir management R&D program, came up with a technique called DDRM, Decision-Driven Reservoir Management. The whole key point around that was just enough model to make the business decision. I think a subtitle would be one of the phrases you had on here is, what do the fluid care about? Okay, that's key. Because coming to think about it, it was not anything we ever used. Okay, but that's where we were going. What did the fluid care about? If you go back 25 years ago, the industry was trying to seek truth through building bigger models, precisely wrong bigger models. Okay, And so our philosophy was just enough model to make a business decision. And it's all very consistent with what you're talking about here, and it's brilliant.
Thank you. And this,
Oh, by the way, one more point. One of the members of my team there was Mike King, you referred to. So,
yeah, and if you can't draw it, don't model it. Apparently, this goes back to Glenn Williams from BP. That quote, but it has
he was another member of my team there
Good.
too. Mike King, Glenn Williams,
probably Mike Christie then as well.
in and out. Yeah, whether I could afford them from one year to another.
But there's another. If you go for quotes, like the worst thing that can happen is, at the end of the day, you end up with two things you don't understand. It's a reservoir and your reservoir model, and that's what we try to get around here.
Okay. Question online here from Tsuyoshi Matsura. I guess it's picking on Rick again. Thank you for a nice presentation. Is it possible to determine the efficiency coefficient Rick was talking about with RRM?
I haven't thought this through, other than sort of last night when I started putting these 2 extra slides in, and not to pick on Rick, because I think what you mentioned, Rick, in all seriousness, was really, really important. We have so little data, and there's so much things we don't understand, and hopefully this can help you to understand. It may be possible to get at least of a ballpark figure, is it 2.65, is 2.85, get that sorted out. But this is for much smarter students to find out than Rick and I could ever be.
Yes. Okay. No more questions. Once again, thank you, Dr.
Thank you very
Geiger.
much.